I guess we'll get started. And so I'm slightly concerned about attendance, honestly. So is that normal that like only get like a quarter of the attendance? So if it's normal, then it's fine with me, honestly.
It's just real cold.
Okay. Yeah, but no. I mean because like last semester or last year, like last offering is like that also. The worst case, as I mentioned, is like 2 out of 30, like not as many as this class. This is like near 40. So, but I kind of like, but it turns out the review is okay. So I'm not sure. So is that just common like that? Then it's actually okay. So, but I'm just a little bit concerned if I did anything wrong about that. So, just share with you guys another story that like, I finally got money from the company. What I did, like I just need to like stop answering the messages and picking up their call for like an hour or so. Then afterward, they quickly pay whatever bill, like the due payment or something. So I guess it's difficult to be a good boy always. Like after a while, like that, I realized like okay, I need to change the strategy and somehow, and so that's why I think empathy is really important. Like empathy is not the same as sympathy, right? You know, empathy is really putting your mind into people's minds, like feel what they feel and think like what they think. So and it's not only that I'm not saying that I should take advantage of that, but like if you can really think, understand what people is thinking, like it's really extremely powerful. Because after a while I realized that okay, these 3 guys there, who of them like these guys are actually probably my ally, and this one I don't know what he's thinking anyway. So, but and then you need to understand whether they need you or they don't really need you. Of course, what I did is kind of risky also. Maybe I would, but it's okay, just 1 month. So I stopped picking the calls, and then maybe they will get mad and they just stop the things completely. But yeah, but sometimes you just need to guess a little bit, like with certain probability. I think it's likely. I don't know. So anyway, and what else I want to say before getting into this thing that I know that once I get started very quickly, you guys will get a bit distracted or like sleepy and so let me. Okay. Actually, there's a couple of things I remember. Last time I mentioned, right? Like I made a mistake with that company. It's like it's like there's a Chinese saying. I'm not sure even it's a Chinese saying because it's really a Cantonese saying. Like I'm from southern China. That is actually Chinese is really okay. Now I'm getting into like not exactly anything related to here, but it's like okay. Probably not politically correct to some Chinese, but I really consider Chinese as a group of languages instead of one language. And in this is so. When I speak Cantonese and Mandarin, like it's basically far different, like from let's say Portuguese and Spanish. And the Cantonese saying the last time I want to say is like I can't even translate that, but I find the word for that. I'm looking for that. That's in the past you have like some male got neuter just to serve the emperor. I think the word is you know this word unique. Yeah, that's the word. That the saying I would write it down just for fun.
There's a show called Game of Thrones.
Yeah.
And, it wasn't the Spider Master either, right? It was very.
Okay, my writing is horrible, and in terms of like, I'm surprised that I can write Chinese, because I didn't do it like since what 20 something years ago, because you can type, right, or like something like that. Okay, so that saying is like, okay, in Cantonese I say once 皇帝唔急太監急. So this is the emperor, this is the eunuch, and this is a hurry. So I'm not sure how to translate that. Hurry in the sense that you feel that this is urgent and stuff like that. And this is basically no, like something like the emperor is not hurry about that things, but the eunuch is really worried about that. That's what I'm saying. Like they said that okay, we had that deadline, and then we want to do it like in 5 days or 10 days, and then like okay, I will send it out as soon as possible. But then yeah. So anyway, then this is actually it's a pretty good proverb I found. So okay, I really need to get to something really serious, not as exactly really serious, but let me continue like a little bit what we talked about last time. That we're trying to for the last couple lectures do some picture finding over the images, and then match the key points. Actually, first find the key points, and then like for each key point find the descriptor for the key point, and then match them, and then like yeah, you can warp the according to how the key points are located. Then you can do a image stitching, right? So let me just give a kind of demo to put things together. So here. I'm not using library at all, so but it still works well. I mean, in the sense that like it's not the ideal descriptor here. I'm not using exactly what I'm saying, like very nice key point finder. Also, like I just use a Harris corner detector here. So just say like, and I have two flag here saying that like whether I'm trying to have the transform, warping the transform is affine or not. And if you remember the last time at the end when we talk about like a method called ransack, it's just trying to exclude outlier. So you may need to get back to the notes because this probably will be the homework 5. So it's trying to do the stitching. So you can use any kind of key points, extractor, and like descriptor there, but I just want you to avoid the warping part. Just like after you've matched all that, like you warp one image and another image and kind of put them nicely. I probably will give you code for put them to display them, but you need to warp them basically. So here I have several images. I already put a note for that, like for different kind of images. I have this village. Maybe I will use a harbor image. Let's see. So and this is one of the image here, and it's basically just a Harris corner detector. I'm not using SIF even. And this is like another one. It's also like. I think I'm using Harris corner detector, and then here this is I call my SIF descriptor, but it's not SIF at all because it's basically just HOG. That will be you will try to implement in homework 4, and then that couple lines here find the scores there, like just the match score there, like for each of the descriptor with the other descriptor of the match score there. And here I will give you the, actually in that case maybe I already give you the answer here anyway. So this will show the, Oh no, not yet, because there's a one sec there. One sec is not showing. But that's bonus one sec if you want to implement that. So as you can see, it's kind of okay. It's pretty nice. So we warp like one image here is showing like all these match points here. And I see this is basically the same thing, showing how which points is matching which points here. So we may play with that again, like starting saying that if I'm not using one sec, and if I do this over again, let's see. Let's see. I think it failed actually if I'm not using one sec. Yeah, it completely failed in this case. So in this case, actually because maybe my descriptor is not. If your descriptor is more, what I want to say, more robust, maybe. In that case, maybe you can get around with the one sec, and also like because I'm using the perceptive transform. If you remember, like when we are using the we have the warping there. Let's close this thing. We have the warping there that so basically we have the original coordinate, right? So we have a warping matrix to the new coordinate, like x pi, y pi, w, let's say, or whatever, and or maybe I say hat or something. The actual coordinate here, of course, will be like x hat over w, y hat over w in terms of Cartesian coordinate. And if I am saying affine, then basically this part will be non-zero. This is 1, and this will be 0. That will be affine transform. For affine, you are just basically will warp the whatever your coordinate into parallelograms or stuff like that. For example, like is this called parallelogram? I think it's still called parallelogram. So this will warp into something like that. This will be parallel, and this is parallel, stuff like that. But if I go for perceptive transform, then these two coefficients will be non-zero as well. So and actually, like the first example I gave you is a perceptive warping, but with one sec is turned on. If I turn off the one sec, that doesn't work. But if I use affine transform, maybe it will work, because affine being a bit more restrictive. Let's see. Actually, still not working. I think like I have one of these images. If I use, no, I didn't change to affine. This is affine. You can say it's working. I mean, kind of not working very well, but it's kind of like okay. I have one of this image work better. Let me find the one. I think the village one is easier. That actually it works even just with affine without one side turning on. It's still pretty bad. But so in any case, it looks like I really need to turn on like one sec. And if I turn on one sec, am I there yet? Yeah, you see like you can't make the match here, but because I'm using affine here, so you may not see clearly that when I warp this image on the left, this is actually, after the warping, is still a parallelogram here. This is not the boundary, this is the boundary. So so because it's only warping to a parallelogram, it cannot kind of match exactly. But let's do it a final try here for this image. I have is perceptive, transform, there's the whole transform, and also one sec is on, then again it's pretty nice. So that's basically something for homework 5. I'm not sure I will have homework 6, so that may be the last homework. Maybe we'll see about that. So yeah. And today the main thing I like to talk about is optical flow. So maybe I can show you a kind of not exactly a nice demo. I just copied that from. Oh, that is actually already the directory. Yeah, I just copied from some OpenCV demo. This I didn't make any changes at all. This is an example you're expecting. It's basically trying to, for each of the adjacent frame, it try to check like what is the apparent movement of some pixels there. And here it's not doing a dense optical flow. So in the sense that it only pick points that is top, like it's like the fish points or like key points there, that you pick the points that you know more precisely the motion is there, and then it's just plotting those. You can have also like dense optical flow method. Actually, I will talk about that. Like this Funderback method. This is like something add-on, like compared to last year. I didn't. I was thinking whether I want to talk about this because I didn't implement that. This kind of Funderback method. I went through the paper, kind of understand the high level, but anything that you didn't implement yourself, honestly, it's hard to say you completely understand that. But I guess I will just still talk a little bit about that, but maybe I cannot, address all the questions if you have. And I find it's pretty interesting, like when I'm going through this guy also, like, all of this is, of course, there's two guys, right? Lucas, Canada, and Canada is really famous. Like Lucas is a student. Like this is like in the 80s. This is also this method is in the 80s, like early 80s, and it's like huge number of citations, also like over 10,000 citations. And Funderback, why I went into this because when I look into the OpenCV libraries, now they suggest to use this algorithm instead, like and. For dense optical flow, the demo is using this Funderback algorithm. And I'm not sure like I should call it Funderback or like Ghana Funderback, or because this is actually one person. I dig into his PhD thesis. It's quite well written actually, and he graduated in 2003 or something. He's a Swedish. Is that how you call people from Sweden? So and I was kind of curious though, like, because he seems to disappear since 2013. So I'm not sure he's get out of the academic research, or like he's just like kind of died early or something. I don't know. Because that happened actually. Yeah, that happened. Yeah, in academia especially. I remember that's one pretty famous Sam Roweis. I don't know how to pronounce his last name, but he was a star in 2000 something. He has some paper in Science and so on. He has this yeah. Anyway, then one of the day he just jumped out of his high-rise building, and he worked in New York City, New York University, I think. So I don't know. Anyway, the mental health is really important, by the way. Yeah. So don't be too stressed out. If you guys are too stressed out, just let me know. So I am a very relaxed person. I can give you some advice for that. Or I should say I'm really laid back. And so anyway, for optical flow. Oh, actually, another thing it's also just out of my curiosity, like because I watched documentary about like higher education in the U.S. And the student debt problem. Like, how many of you are having student debt now? Student loan and
Student loans?
yeah,
Oh, yeah, I got student loans.
like all of you guys are in debt, like for the
Yeah. Yeah.
yeah. So that yeah, that's
Just big weight on my shoulders.
yeah, that's pretty. Yeah, I don't know. Yeah, it's getting really expensive. I'm really curious. This kind of like, I also kind of curious. Like, is this really sustainable? Yeah. But anyway, like I hope you guys don't feel that like your money was kind of wasted. At least hopefully not for my class. And yeah, I'll try to do my best like to give you things that is actually useful like for your future. And I hope still convince you that about homework that you want to implement stuff from scratch. And somehow I still don't know like whether it's for that reason also because I always learn to stuff this way. I think it pay off a bit because I still like my students still get stuck for his code. I don't know. I tell him okay. If you don't want to continue on that, it's okay because the company say that at this moment it's okay to go with MATLAB. I can just send me my code instead. But then now he got frustrated and really want to fix the bug or something. So anyway, and of course, when company asks you to write a code, like most likely they really need the kind of like a distinctive method that is not already available in OpenCV and stuff like that. If it's really, you can really put this and put it there, then they don't, or like maybe they have open source. In my case, I'm actually I can talk in one of the lecture about what I did like for that. But maybe in one of the class, if I have by the end, if we still have time for that, it's actually pretty interesting. It's like they have this. I forgot whether I mentioned that they have this new kind of cameras, not exactly new, maybe a decade old. Like they started from Stanford. Like it's called light field cameras. Maybe you guys have heard of that before because it had a commercial product there. The company is called Litro. Like the PhD student, he graduated about around 2006 or something. His thesis even got an ACM award. And then apparently he's very smart and he started the company with some other fellows. And basically the camera is like, they just are simple cameras, but they have some micro lens array on top of that sensors there. What's going on is like, instead of like you have, each pixel is like detecting the total amount of light, right? So instead you have a tiny micro lens on top of a group of pixels there. So then the micro lens can basically, or in the sense like the group of pixels behind the micro lens will detect light behind the lens, not just for some of all the lights there, but also like including the directional information. So therefore, it's like you can capture images not just having the total amount of light, but also like where the light is coming from. So taking those information, you can do some interesting processing. For example, his killer app there, like he was thinking, okay, I will build a camera that can do post focusing. So you take the photo arbitrarily, but you can focus whatever you like to whatever. And they had just two products. And they folded like after two products. They got bought out by Google, so I'm not sure it completely folded, but it's not a really good price. I guess it bought out by, I forgot, like 40 million or like 80 million. because before that people were thinking like at least worth like 700 millions or something. But they have the final cameras. You can still buy it like on eBay, maybe $300. But when they brand new, when they sold it, it's like I guess 1,200 or 1,400, I forgot. And it's a kind of high-end camera, right? But the problem is like the resolution is not that decent, because like you have this micro lens on top of a bunch of pixels there. So the real resolution will be the number of micro lenses, not the number of pixels there. So you basically decrease the resolution somehow. And for the camera, the resolution is only maybe 4 mega something, and it's not acceptable. It's just several years ago. So anyway, then, but you can do lots of interesting processing with those cameras. Anyway, yes, go back to here. So we are going to talk about this optical flow. As you see, basically like detect like what the things is moving, right? But it's like not in the sense it's really we can detect exactly what the things is moving. It's like just apparently to us like how they are moving, because you can think of a TV. Also, a TV there's no motion. Right? You look at a TV screen, like what's going on. There's no motion, but you will just predict those virtual motion there. And as I mentioned, it's just apparent motion there. And if I have a dense optical flow, will be have this kind of feeling, right? And so basically, like you have multiple frames. Let's say I have frames like previous frame and this current frame. So I want to know like for each of the pixels how they move like this. So I need to find these vectors here, and it's like you can consider this motion here for each pixel is represented as like some kind of fancy motion field there. So and I use a U and V to represent that, and that we need to put in some assumptions for these things to work. First of all, is like we want to have the brightness is kind of consistent, right? So for example, like if I have this object move to here, I don't want to in the next frame it just like change the color or the intensity completely, and the motion is supposed to be small, like it's reasonable, and it's kind of spatial coherence in the sense that like if I have why my pen is already gone. If I have a pen is not working, so okay, it doesn't matter. So what I mean is like if this pixel is moving into here in the next frame here, the neighboring pixel supposing also moving like similar direction, something like that. That would be the spatial coherence. And this is just repeating what we're saying, like small motion shouldn't move that far, and spatial coherence, it makes sense because if you look in the same object like in the scene, then everything like on the pixels on this object should move accordingly, like in accordance. And brightness consistency is reasonable if you don't, the frame kind of like the time doesn't change too much, or like you doesn't have suddenly change. Well, of course, if your lighting suddenly change, you kind of screw up your optical flow for at least for that time instance. And so with this assumption, then we can just write a constancy equation here. So this is the intensity of the image for pixel x and y at time t-1, and at the next time instance, since I moved by u and y, right, u and v, right, so it will be just a very simple equation like this. Then we can use Taylor series expansion. That is actually basically the same trick, right? We use this many times basically. So if we do a Taylor series expansion of this guy here, so it will be something like this, right? Supposing U and V is kind of small, it will be like this. So this will be, since this will be equal to that here, that's saying that like this thing here will be should goes to 0. Right? This should be approximately 0. And I can write into a matrix form, or like it doesn't really necessary. And that's for derivative, like yeah, of course we can just use filter to compute that. Like this, as you can see here, we can have different filters to compute derivative. But of course, the problem here is like if you look at this equation here, I have unknown U and V, but I have only one equation here, right? Because this is actually a single equation. This is a scalar here. What I mean is this is a vector, this is a vector, plus this is a scalar. This is actually just one equation, but I have two unknown here. So of course it doesn't work. I'm also like that's another problem, as you will say. But this problem is that you can't help it. But let's just look at this anyway. So in the sense that like if you are near the edge here, so and if there's some motion in this direction, you cannot tell whether it's the direction is here or like here. Yeah. For example, like this kind of like you can say it's a kind of aperture problem here. So if my line here move like this here, right? So it's like moving in this direction, right? But what I can see is I can only visualize in this direction. Yeah, but this is not something we can solve. We will solve like what we can solve. So so let's start with the first method to solve this this constancy equation. I forgot baseless constancy equation. So of course, as I mentioned, we only have one equation, but we have two unknowns, right? So the simplest idea will be simply we use this spatial coherence constraint. So assuming that like for all the labeling, pixels will have the same direction. I'm just like then we will have more than one equations with only two unknowns. So for example, we can like say like with a 5x5 windows, and then we will have 25 equations there, right? 25 equations, two unknowns. We definitely know how to solve that. So again, like going back, like this stuff we keep repeating. It's like just this square method. So we solve this U and V, and then the solution will be simply. Of course, I can write down the solution right away as like A transpose A inverse A transpose B for that. So, but before that, like we may want to also look at this equation here. I have this A transpose A UV multiplied by this A transpose B here. This thing, of course, if it is invertible, then I can immediately pull it to this side. But if it's not invertible, then it won't do much help like moving to this way. So maybe that before we even like move this to the other side, this time we want to do one more thing. It's like we want to see like whether it's good idea to say the solution is just UV is equal to A transpose A inverse times A transpose B here. We want to check whether like this makes sense. Moving this to the other side makes sense. So as I mentioned, like it makes sense only when this is invertible, right? And we can go even a bit further. It's like if it's not well conditioned in the sense that like if one of the eigenvalue is too small compared with the other one, that's kind of bad also. So therefore, we want to have like basically both eigenvalues to be big of this matrix. If that's so, then the inverse will be pretty stable. Actually, if you look at this, since you're doing this homework 2 or whatever, that is actually very similar to the highest common detector. That's exactly the thing that we're looking at. So, and we can jump ahead here. And that's basically saying, like, we're actually looking for, therefore, like, this will make sense to move this A transpose A on the other side to make the inverse. Basically, when it's a corner, right? So actually, it can be making sense, right? Because when you have the place that the region you're considering is basically flat or is an edge, then as we mentioned that like you can't really predict the motion correctly, right? So only when you are near the corner actually you can predict it really precisely. And so therefore, okay, this is just repeating the argument. So yeah, that's basically just repeating the argument. So so therefore what we can do is like, as you see like in the first demo there, that you see when I have the car moving, this is exactly doing that. It's like it try to just show the region that like the solution is accurate. So basically it's only showing solution that is in the corners. So that's both like the lambda 1 and lambda 2 for this A transpose A is big. But we can try to improve the algorithm a little bit more. So one possibility is that like we can if this is not exact, right? This is not exact, then maybe we can fill in some higher order term for that. So in that case, it will be like looking for solution. It's not just first order, but like high order. Then will be like kind of like some rely on some polynomial like algorithms for that. But actually for maybe Newton's method or something. But we won't talk about here. But what we will look into is we can simply like use the same method, but we reiterate that many times. But when we reiterate that, it's kind of similar to like looking into like high order solution. So therefore, like one possible improvement is like first you just do the Lucas Canada algorithm that as we just discussed earlier. That basically UV is just again is the least square solution, the A transpose A inverse A transpose B. And then afterward you have this UV approximation, right? You use the UV approximation to warp the image to the new location there. And with the warp image, you try to estimate the warp image with the target image again, and you keep repeating that. So then this will give you a kind of a better refinement. So, okay, that's Lucas candidate. Any questions for that? So, and probably no. Typically, when I ask any questions, there will be no questions. I don't. It's really rare, like 1 out of 100. That any questions, there will be some questions.
What was the effect of noise?
Probably pretty bad. Honestly, I didn't pay enough of that to answer you like intelligently. But if just looked at the algorithm, I guess it would be pretty bad. If you're really noisy, like, if you're, but I guess that won't be if. Okay, first of all, you can always just do a small filtering before that, right? And also, like another tiny fix is you can even, if you remember the gradient, all this gradient, you can also have a filter gradient instead of the gradient directly, right? And actually, if you increase the patch size itself, is already some filtering effect. So therefore, like. Of course, if you are really noisy, then really it won't help. Yeah, and let's look at the second method here. I'm not sure how to pronounce that. Schkung or something like that, maybe. Is that a German? I don't know. Schung?
Yeah, I think that's Schnuck.
How to pronounce it? Schunk? Hornschunk? Schunk? Oh yeah, I'm not sure.
It's German, right?
Yeah, so, this method is a little bit different. It's actually about the same era. So both of these are really famous, both of these methods. This one, instead of he's using a kind of like a labeling pixel, assuming all the labeling have the same kind of direction of movement. Here, you just use a kind of simple regularization, kind of additional cost here. So in the sense, it's assuming like your UV doesn't change quickly. So it uses the other assumption. It's basically like it enforces that UV is kind of small. So a small changes, or I shouldn't say UV is small. It's small. UV is small in changes in the spatial direction. So it's kind of similar also. Like I shouldn't say like it's different. It's also using this spatial constraint there, but the result will be a little bit different. So so here it's the same thing, right? This is the constancy, like Binet's constancy equation here. You want that to be small. This one, as I mentioned, this just enforces UV doesn't change quickly, and then this alpha is just some hyperparameter there, and then here, like you want to now, therefore, like we have this total energy function. We're trying to minimize this total energy function, right? And UV here, UV is basically a kind of a function of x and y itself, right? So therefore, it's actually quite complicated here, as you can see. Like this is actually a so-called functional problem because it's a function of a function, right? UV, and if I don't know how many. You guys must have taken like a couple calculus class, right? Do you remember you take anything like calculus of variation? So this is like in the RAM. I always don't know how to pronounce it. RAM, REALM, how to pronounce that? In the area of like calculus of variation, and so but the idea is actually not that difficult. So let's say I put this is some kind of function, right? Or like functional, whatever. If I want to say more precisely, a functional with this u and v here, and uv themselves is a function. So now if I try to kind of find the optimum for this L with respect to uv. Let's say this is the optimum there, then I should have consider any arbitrary function like u tilde and v tilde, and I shift uv by away from this u tilde and v tilde. And this thing here, you look at this is kind of like similar to a derivative also, right? If my epsilon is tiny, really tiny, then no matter I change to what direction, this value should be kind of 0, right? Because if I at the optimum there, let's see if I can write still. I cannot write earlier. I can write this time. So because you just think of this as like a derivative, right? You have this L now, then you have this UV direction. So you vary along this UV direction, right? So you have like U, if this is the optimum UV here, and you change to add some U tilde here, and then like if this is optimum, this will be flat, right? So therefore, if I make tiny changes of U tilde and V tilde here, and I over this epsilon here, it will just equal to 0. So So because of that, let's look at this difference here. This difference here. This difference, again, like it's always just simple calculus, like Taylor series expansion. Let's expand with the first order derivative there. Like so, then this expansion, like in the first order in terms of epsilon, because epsilon is smaller, epsilon squared, the terms I don't care. So epsilon, then I should take the derivative with respect to u times epsilon u tilde, right? So therefore I have this term here, and with respect to v times epsilon v tilde, so I have this term here. And now remember that like when we change this at this u tilde here, and this L is not just a function of uv, okay, it's not just a function of uv, it's also a function of like derivative of uv, right? Because this gradient is basically ux squared plus uy squared, right? So therefore, I also need to take partial derivative of these guys here, right? Take partial derivative of this guy here and partial derivative of this guy here. And if I take partial derivative of these guys, I need to add back what's the change of like ux u tilde x there, because if I add u tilde there, I will have u tilde x, that additional derivative for of u for with respect to x. It's hard to say. So same for like v also. So I have this 4 additional terms as well. So this is all the first order terms here. So then I subtract this guy, that this got cancelled, and remember, yeah. So I have that. And then like this here, I can do some expansion now. So I take derivative of this guy here. I have with respect to u, but this have no u here, right? So that if I take derivative of L with respect to u, that's this will be nothing here. But I have 2 times this guy here, ixu plus iyv times it multiplied by ix, right? And this should multiply by u tilde epsilon, and so I have basically this term here. And also I have take derivative with v here, then again have 2 ixu plus iyv plus it, but this time I have iy here, and multiply by v tilde epsilon, so I have this term here. So similarly, I will have all these terms here. If I, for example, I take ux, takes this L things with respect to ux here, I'll got like 2ux alpha square. Now I should multiply by what? Multiply by ux tilde epsilon. So therefore I have this term here. So okay. So that therefore, like if I go back to this guy here, this guy is basically this epsilon I got cancelled, so I should only have this here. And it looks a bit ugly, and we can simplify it further. So by the way, I'm going to the first principle. Actually, this kind of problem people typically explain it along the way, called like Euler-Lagrange equation. This is actually a special case of Euler-Lagrange equation, but actually you can go by first principle, as you can see. And actually I think it's easier to understand just using first principle. And now I have this here. The next step, I use integration by part. If you remember, it's something like if I have this ux, for example, if I ux ux, okay, just look at one of the term here, ux tilde dx. If I take the integral there, what I can do is say I first absorb this guy in here. So I have, let's see if I do that. Oh no, in this case actually absorb this ux tilde this to this here. So I become like ux dux, du tilde this is with respect to x actually. Then this is equal to u tilde ux minus u tilde uxx, something like that. So then, and this term is basically equal to 0, therefore we only have the minus side, the later term left, so we have this guy here. So basically, integration by parts for all of these terms here, each of them will give me a minus of this u tilde uxx. It's basically from this one here, and from this guy I have u tilde uyy, and so on and so forth. So then with that, then I can let's see, I can regroup the term here. So I regroup the term, only have the u tilde and v tilde here, and this is equal to 0. So and remember, like what we have from the beginning, we want this to be 0, and u tilde and v tilde is anything, right? So therefore it's saying that like this and this must be equal to 0. So therefore like I have these two equations here coming out. And this gradient square is basically just Laplacian, right? So you can kind of implement that with kind of Laplacian filter will be something like let me remember, that's what something like that, right? This can be the Laplacian filter. More or less like that. Maybe I'm wrong, actually. But that is essentially like this, right? It's basically the average of the neighborhood minus the current values here. Here actually maybe it's better I put it like 1/9 and this or 1/9. Sorry, and this should be like minus a/9. Then that will be exactly this guy here. So okay, I'm sorry about this handwriting here. Everything outside beside the center is like 1/9, and the one in center is like minus a/9, something like that. And then like okay, we have the Laplacian can be implemented like that. Then we substitute that into these equations here, right? So if we substitute that, then we were rearranging the terms. Then what we have is basically, let's see, wait a sec. Why I think I'm skipping one. Okay, anyway, so then with this is basically just a linear set of equations, right? So I have UV, we can start with some UV approximate, and anyway, you can start with like assuming everything is zeros, right? Assume zeros here. Then you can solve this linear set of equation to find UV, and then from every point of the UV, now you can compute the mean of UV, right? And with that, like you reiterate it many times. So again, you can solve the optical flow. And for this one, this is just a kind of like an improvement for the original one. And I won't go into detail for that, but the idea is simply like instead of using a quadratic kind of cost regularization factor here, it replaces that with something like this. So and by the way, why do you think that this is better than this, the original one? So if think about this regularization, what it's trying to do again. Like this is saying that if I add this, if the UV changes, the labeling changes, if it's big, then I try to discourage that way. But the problem is that here it may be too unforgiving, because if you have this spatial consistent kind of assumption there, but you also have like multiple object in the scene, right? So in the sense that when you have like one object here and another object, or like you just think of like this is one object and it's moving in this direction, and then this is just the background here. So then the edge of this object here, of course, is like not continuous, right? So and we expect there would be like a pretty big changes of U and V like across the edges. The original kind of implementation could be a little bit unforgiving, because this is going kind of pretty steep, like for large UV. So this is kind of like this shape is saying that okay, if it's really big, but up to a certain point I just don't care. So so anyway, and finally let's also look at this Garner-Feinerbeck method. So it takes a little bit different approach. It's still like everything is like basically the same idea. Like you have this constancy, Byte-slash constancy assumption there. But the thing is that it's trying to model the image as a quadratic function now. So you model the intensities of a quadratic function. So let's say this is the image, first image, I have one quadratic function like that, and I have image 2 have another quadratic function like that. So if you look at that if I look at D, it's basically the optical flow there, like from image 1 to image 2, at the pixel X there, then I substitute this, I'm expand whatever for this equation here. As you can see, like this term should match with this term here, right? So therefore we have like B1, B2 is equal to B1 minus 2 to A1D here. So, or simply we have something like that. Also a very simple equation. If we can kind of really model the intensity as a quadratic function, of course that would be the first assumption. And of course this is a pretty crazy assumption, right? Because how do you expect like the image will be if you model like this, then basically the image can only be like this kind of shape and nothing else, right? Yes. But what we can do, of course, we would like to there is also changing with locations. So then in this case, we can really model image intensity with like this quadratic function here, given that your A matrix and B also like vary with location. So then in that case, basically we will have just using the same notation previously, we basically have a different problem instead, like this. Not exactly different, but kind of a modification like this. And then of course if we have a different kind of like AX like everywhere, again it's not feasible. So what we can do is similar to Lucas Kennedy. Also we will just consider a window instead. So then instead we try to minimize this. So basically the windows will be also taking a neighborhood around like the pixels we are interested in, and we can also like apply a weighted sum there. So like if the windows is the neighborhood is like farther away from the center, then the weight will decrease more. So then we will have basically and again the objective function is like this. We're trying to minimize the difference here, so difference between this guy and this guy, and weighted by the weight I just mentioned earlier. And And since we saw this many times now, so you know the solution right away. This solution will more or less will be like this, will be the half pseudo inverse, but also like will be a weighted sum somehow. I dropped this x here, like just like in his paper, like it would be like very messy otherwise. So they have some x index like for of this w and a and so on, and so also like for this a and b here, and he mentioned in his paper and his thesis, he also mentioned there's some further refinement. Basically, like for the x and y, for the displacement there, like we were trying to solve for this d, right? We can further parameterize this d into some kind of a polynomial function as well. He picked this one, but he didn't explain quite a bit like why he chose this pick, but I guess at least it's kind of second order, but I also actually I have my own question. Is like why he doesn't have picked to use like same coefficients for these guys here, but you know, I cannot find. I don't know. Maybe you guys have some idea later on. You can tell me what was your thought, but I don't have a good explanation for that. But anyway, he picked this model. So then if he picked this model, then now this is the parameter, and your d is basically modeled by this parameter. And then instead, again, instead of this guy of d, like you have sp instead, and you're essentially solving a similar equations, but just you solve the p, and you have more restriction now. D is less degree of freedom, so it's some kind of regularization again. And finally, he also mentioned that we can make it an iterative approach as well. So, for example, like once we do it once with an approximation of this d, right? So we can do a refinement, or like if we have some prior knowledge of this displacement field, we can take advantage of that by just adding that to what we have there as the prior. Okay, yeah. I mean, like instead of like this, if you remember the earlier equation, this would be also x as well, right? So instead, I would first like also warp that a little bit, like for the second image, to the new location. That's the location I expect that like that is actually already kind of more. The two images match a little bit better. So I will use that to approximate the A instead. And also for the B here, I will kind of adjust that by adding the warping part as well. Let's see. B. Yeah, here I'm not completely sure, honestly. Yeah, but if you guys are interested, like yeah, maybe next time I can talk if I figure out like whether it. At this moment, I have a little bit. Wait, does it make sense? Let's see. AX, this D is the prior field there. And B is the, yeah, I think probably makes sense if I write out all the equations, but I have the feeling that you guys won't be interested to see me writing all the equations there. Okay, so anyway, this is a quick this explanation of this Frontenberg algorithm as well. So again, like the idea is actually quite simple as well. It's just like he has this pretty much a different idea that like first we model whatever image as a quadratic function and basically doing the same idea as previously, do the matches, and then it's a least square method and find the d and then get a little bit refinement basically. But it is a pretty good method apparently because OpenSeries use that. And finally, let's just maybe like a quick mention about like scale problem, because one thing we always mention that we have a small motion, right? But you have objects that is like both fast and sorry, not fast, like far and close, right? And then in that sense, like the motion doesn't necessary to be small. For example, in this case here, this tree trunk like actually moved pretty drastically compared with the background there. So what we can do is say a very simple idea is we can use pyramid, right? That we learned like in the past. We can have pyramid, Gaussian pyramid with different scale there, and then at the lower scale, then we start with working on that whatever you use LK or like any of optical fold algorithm. Afterward, then you know what is that approximate optical flow, and then you can use this to warp one of the image to get a better match, and then the next level you repeat that, and then move to next level and so on. So, and a very simple idea. So this is like, without this kind of pyramid, you see like the tree trunk will fail pretty badly. And if you have like pyramid, then it's more or less you get the right optical flow. And finally, just some quick word for some applications. I don't know. I guess I'll just show some photos here. Like it looks interesting. I'm honestly a little bit tired. I think you guys are also. And I'm pretty sure you can imagine there's lots of applications, right? Because you have whatever you do, you have the videos, right? 2 videos, you have like adjacent frames. You can find all the apparent motions there. That's just afterward you have all kind of like just out of your imagination, like what you can do with all this motion, apparent motion there. For example, you can do background subtraction, like you find exactly what is the object is moving. You can do segmentation, like just group that object that's moving together as one segment, and you can track objects, and you can detect like motion of a person, and so on and so forth, basically. And this is another example of tracking. So I guess this is about time. I guess I'm about to stop here. Only I guess finally just a little bit remark of limitation here. Apparently this is just the apparent motion. For example, if you look at TV, there's no real motion in the TV, but you run your optical flow algorithm. Of course, you can detect all this motion in the picture there. And there's other like similar cases that will have this kind of effect. So anyway, that's the final scene that like you can see some optical flow here with the motion. Do you see the stuff moving? You did? That's weird.
It is moving.
Yeah, it's moving. You look at some of the center here. Yeah, yeah, kind of. It's like rotating. Oh, maybe depend on your angle. Maybe your angle is a little bit. Probably people in the center will see it more. Oh, and next class, I don't need to talk. So, again, you guys will need to grade your speaker. Don't forget about it. I will post on Canvas as some kind of quiz or something that you will rate your speaker next week. Oh yeah, I guess maybe on the computer it's more obvious. If I look at this here, I definitely see that is. I guess maybe
Okay,
when it's
yeah,
closer,
yeah.
it's,
Yeah, I see it now. I see it.
definitely is very weird. Our brain is very weird.
Yeah, I can see it.
It doesn't make sense.
Yeah, I see it now. That's more sense.
Any difference in the angle or
Yeah.